The goal of statistical work is to make rational conclusions or decisions based on the incomplete information we have in our data. This process is known as statistical inference. In inferential statistics, we want to be able to answer the question, if I see something in my data, say a difference between two groups or a relationship between two variables, could this be simply due to chance, or is it a real difference or relationship? If we get results that we think are not just due to chance, we'd like to know what broader conclusions we can make. Can we generalize them to a larger group or even perhaps the whole world? Or perhaps our results support a theoretical model. And when we see a relationship between two variables, we'd like to know if we can say that one variable causes the other to change, or if we just think that the two variables are associated with each other. Whether or not we can answer these questions, the methods we use to do so, and the correctness of the conclusions that we can make all depend on how the data were collected. In this video, we'll look in particular at how to collect data to ensure that we can make generalizations from our data to the group that we're interested in. A fundamental feature of data is that they naturally have variability associated with them. We've seen how we can picture the nature of that variation in box plots and histograms, and how we can quantify it with summary statistics such as the interquartile range and the standard deviation. In the process of statistical inference, we can imagine that we have a real world where we have our observed data, and a theoretical world where we have scientific models that we think give plausible explanations for how our data arose, and statistical models that explain the variation in the data. The inferential process connects what we've observed in the real world to what we can say about the theoretical world. Often we're interested in making conclusions about a particular group, which could be all people, or all Canadians, or women aged 15 to 25, or whatever else we're studying, such as countries or skeletons. The group we're interested in making conclusions about is our population. When we collect data about the entire population that we're interested in, this is called a census. Most countries carry out censuses on all people living there every few years in order to better understand them. But in most situations, taking a census is impractical because it is too time-consuming or expensive. Sometimes it's also impossible. In some situations, such as testing a manufactured product, it might be necessary to destroy the item in order to study it, and a census would then be impossible. When we can't conduct a census, we often collect data on a sample from our population, and our goal is to make conclusions about that population. In this case, our population corresponds to the theoretical world that we're interested in. Our statistical model can be used to describe the variation in the data in the population, as well as how statistics we calculate from our data vary from one sample to what we would have had if we selected another sample. A typical example of this is a poll. Our population is all people living in an area, and we're interested in what they think about an issue, or how they would vote if an election was held that day. A poll would ask a sample of the people in order to make conclusions about the opinions of all of the people, or the population. Recall that a statistic is a value calculated from our observed data. Typically, a statistic is chosen to estimate a feature of the theoretical world or the population. The feature of the theoretical world or population is called a parameter. We use statistics to estimate unknown parameters. We want our statistics to be appropriate estimates of the population parameters. That is, we want to be able to generalize what we observe in our data to our population. In order to do this, the sample needs to be representative. Even a sample of a small number of observations, if the sample is representative, can give good estimates of parameters regardless of the size of the population. The key to selecting a sample that is representative is to use randomization. Using random selection ensures that we don't systematically exclude or over or underrepresent any part of the population. There are multiple methods of collecting a random sample. The simplest is a simple random sample. In a simple random sample, each possible sample of size n from the population is equally likely to be the sample that is chosen. You can think of selecting a simple random sample as putting all members of the population into a hat, mixing them well, and randomly and blindly picking the sample from the hat. More complicated methods include stratified sampling, in which we take simple random samples from subgroups of the population. Typical subgroups for stratified random sampling include provinces or states when taking a sample of the people in a country, or genders or age groupings, and so on. Stratified sampling is sometimes more convenient, ensures that the characteristics of each subgroup can be examined, and can give more accurate estimates if there is less variation in a subgroup than there is in the whole population. Cluster sampling is useful when it is easier to select groups instead of individuals from a population, and is often a less expensive way to get a random sample. As an example of cluster sampling, if our population is, say, all students in an area, it may make more sense to randomly select schools than students and take our measurements on the students in the selected schools. Cluster sampling is useful if each cluster is representative of the population. For the purposes of this course, we'll stick just to simple random samples. Many samples that are used in studies are not random samples. In a systematic sample, the population is put in some order and then, for example, every 5th or 10th or 100th unit is selected for the sample. This is fine if the ordering has no meaning and if we randomly pick which observation we start selecting on, but it can sometimes lead to samples that are non-representative because there is some structure to the list, such as hidden repeating patterns. In a convenience or volunteer sample, our sample is the units that are available or choose to participate. This almost always results in an unrepresentative sample. Say I wanted to learn about the views in the general population of the importance of statistics, and I asked the students in this course, since I can conveniently reach you, for your view of statistics. However, your view is not likely to represent a population that also includes people who have never taken or do not want to take a statistics course. If a sample is not representative, it can introduce bias into our results. We say that a sample is biased if it differs from its corresponding population in a systematic way. This can result in statistics that are consistently too large or too small. Bias can occur because of the way the sample was selected, or because of the way the data were collected from the sample. If the sample was selected in such a way that we miss or underrepresent part of the population, we have selection bias. For example, imagine a phone survey that only calls landlines. We would miss everyone that only has cellular phone service. Measurement bias, or response bias, occurs because the data are collected in a way that elicit a response that is off from the true value in a systematic way. Response bias can occur because of improperly worded questions that may lead the respondent to give an opinion for or against a contentious issue, or because a question asks about a controversial issue for which people may not want to give their true opinion. Measurement bias occurs because the measuring instrument is faulty in some way. Often people who were chosen as part of a random sample choose not to respond to surveys. Non-response bias occurs if the individuals that do not respond differ in a systematic way from those that do respond. For example, suppose working parents tend to be too busy to answer surveys. Then their views will be underrepresented, which is an example of non-response bias. There are many examples of non-representative sampling that have led to resulting data that are not reliable or representative. A classic example is the Literary Digest poll of the 1936 U.S. presidential election. Literary Digest got responses from 2.3 million people, a huge sample, and based on these responses, they predicted a 3-to-2 ratio of votes in favor of the Republican candidate. However, his Democratic opponent won. So what went wrong? The people surveyed either subscribed to the magazine or owned a car or a telephone. In 1936, this was only wealthy people. This is an example of selection bias. Moreover, this survey was voluntary response, which typically overrepresents angry people or people who want to change, so non-response bias also comes into play in this example. Another example that caused a lot of controversy in Canada, including the resignation of Canada's chief statistician, was related to changing a survey from mandatory response, which ensures there is no response bias, to voluntary response. In 2010, the Canadian government decided to replace the mandatory long-form census questionnaire, which was sent to a random sample of 1/5 of Canadian households, with the new voluntary response National Household Survey, which was sent to a sample of 1/3 of households. Some more households got the survey, but now it was voluntary response. Many groups, including provincial governments, religious, charitable, and business organizations, and the Statistical Society of Canada, opposed the change. These groups argued that voluntary response will lead to non-response bias. For example, one could imagine that recent immigrants may be less likely to respond, and thus they would be underrepresented in the sample. Yet part of the purpose of the survey was to identify the need for social programs, some of which would benefit recent immigrants. Statistics Canada has since cautioned that the results of the voluntary survey are not comparable to results from the previous mandatory response survey, and caution must be exercised when evaluating trends. If our goal is to collect sample data that we can use to generalize about a population with no bias in our result, we need to select a random sample. In upcoming videos, we'll discuss how the method we've used to collect our data can affect the strength of the conclusions that we can make.